Alright, so last time when we were doing introducing this chapter, what was this chapter about? Anybody? We'll start up here, drawing one, and work from there. Mechanical advantage, correct. And mechanical advantage, so let me... I'm not going to write that one out. You guys know it's in the chapter. It's right here. How is mechanical advantage defined? How is it defined, Jackson? The advantage to mechanically move something. Well, yeah, I mean that's basically it. You're right, but I was looking for more of the mathematical version. So essentially, it's a relationship of the output force to the input force, right? So what I put in for there to be a mechanical advantage for the situation, like let's say I need to lift something heavy with a mechanism, and I can't do it myself. The mechanism better be able to multiply my force and make it larger on the output. Or else, like if it makes it less, like if I put it 100 and it gives me 25 out, then I'll never move it, right? Nothing will be moved. So it is input to output. Force. So input to output force, right? All right. So how do we go about this? So how do we solve a mechanical advantage problem from what we saw yesterday? Like, how do you do it? Anybody want to take a crack at it? Like, how do we solve these? Is it something new? Anybody? It starts with an I, an N. Anybody? I see some people typing, so we'll give it a second. Instant centers, yes. So essentially, Jackson, you are right as well. We take instant centers because through the theory that was shown in the earlier part of this chapter, we were able to prove that essentially mechanical advantage is only a function of the mechanism's geometry, right? And by geometry, they mean where the supports are for each part of the mechanism, the input and the output. And we also were able to prove that you can relate these in terms of instant centers through manipulating of the mechanical advantage equation. So, that is instant centers So instant centers, right? And you guys should be pretty familiar with how to do these since we did it last chapter. So the solving of the questions are pretty straightforward, right? Essentially, we just find all the instant centers, the ones we need, and then we relate the input force to the output force using instant centers, right? So we're going to start really quickly on this question right here. We're going to do this one and then the next one, and then if we have time, I have one on another page. Although I think actually the next one's already on another page. Let me see. It is. Cool. Alright, which is this one right here. So, well actually we are going to do two. Alright, so it says this is the mechanical advantage in a slider crank mechanism. So, it says consider the slider crank and mechanism in figure 6, which is this one right here. Input force is imposed on link 2, so that is F2, which is right there. And the output force is applied to the slider right here. Link 4. Assuming no losses in the mechanism, so that means there's no efficiency in this one, right? We're assuming that it's a one-to-one transfer of power. Equate the input and output power as follows. So, right here, this is what we got so far, right? So remember, this is the mechanical advantage equation, right? So, remember, for an input link, it is F2, so this is the force put on the link. D12 is the distance from the force, essentially, to its point of stability, or its point of rotation, which is this right here. This is the revolute joint that it spins about, times the angular velocity, right? Because it's a spinning link. But this question is different than the ones we saw yesterday. And it's different because of what? Anybody want to give me that answer really quick? Why is this one different? So look closely. I will go up here. So up here, yes, so John Lynn is correct. It has a slider in it, right? So it is this part right here. This slider is the difference. So this slider basically means that so the output is no longer a spinning another link that's moving inward or spinning about a point. It is sliding away from us or sliding toward us, right? So if you recall, for sliding joints, you have to label them differently, right? It's not omega 2 or it's not omega 4, right? Because it is not a spinning. There is no angular velocity of this, right? Because it is not spinning. So let's drag it over here. As you can see, it shows F4, which is the output force, and it's times V4, and V4 is just the I think relative velocity, if I recall. I think it actually is just, I think it's just velocity. I don't think it's relative. It might be though. I don't remember how they denote this in this book. If anybody remembers, let me know. But essentially it is the force times velocity. So output force times velocity, right? Right here. So the difference between this one and the last one is that our equations would have mirrored each other. It would have been F4, D14, V4. Or not V4, omega 4. But because we have a slider, we don't use angular velocity. Alright, and then it says, and then it further, manipulates this, so we move F4, we get it into this form, so output for force versus input. So you divide this over, divide that to the other side, and you end up with D12 omega 2 over V4, right? And if you recall, so this is another thing that we have to recall from a previous chapter, is that so D12 is the distance right here. It is just from where the force is being applied to its point of rotation. But then they took this quantity out, right? So let me make that a little more clear. That quantity right there, they took it out, and they replaced it with 1 over F4. How were they able to do that? Why were they able to do W2 over V4 is equal to 1 over F4? Why has that happened? Anybody? I'm going to take a drink while you guys deliberate. Anybody? So, I gave you some time. So right here, if you recall from our kinematic coefficients chapter, right? The kinematic coefficient of a slider or something moving away is F4, right? I hope everybody remembers that. And F4 is denoted as the, it is basically it's V4. So it's the velocity the velocity of that link with respect to the input link, which is d, well, it's this right here. I guess so if you remember, it's this. It's denoted as dr4 over d theta 2, right? Do you recall? So remember, whenever f is being replaced in the equation, it's dr4 over d theta 2. And right here, dr4 is what? So the derivative of r4 is essentially, it's the velocity of 4, right? Would you guys agree? It's the velocity. So this right here is the velocity, right? So velocity right here. So this is v4. And this right here, d theta 2 is what? It is omega 2. It's the angular velocity of 2. So how we were able to replace it is essentially it's the inverse of, just like the last one, right? Is that it's 1 over f4 because these are reversed. W2 is on the top and v4 is on the bottom. So we were able to replace it with 1 over f4. So that is where this part comes from. That's why an f4 is on the bottom there. And then, if you recall from previous chapters again, f4 can be replaced with that. Because if you recall, f4, I'd have to go back to the chapters, but they defined these. I think this was over something in previous chapters. I have to go look. Chapter... whatever. It doesn't matter. You can find it. I think it's in chapter 3. It's the first time we did the velocity and acceleration analysis, they defined f4 as this. If I find it, I'll pull it back up here. I'll move it over because I'd rather show it than not. Oh, that isn't it. No, I think a little further than that. Yeah, so right here. This is what I was talking about, so right here. So when the input is theta 2, this is h sub n, so this would be like an h3 or something. You put it into here, and then this is where they grabbed their equation. It's I12, I2n, and n in our case is 4. So I'm actually going to keep this open because that's rather helpful. So that's where we get this from, was a previous chapter. Because the kinematic coefficient of link 4, since it's a sliding away, it's moving further or backwards, or forward or backwards, it is done as this because it has an input of a theta. And so when you put it all together, you end up with this equation for mechanical advantage, right there. So, that equation is mechanical advantage for us. And so real quick, I'm going to try my best to actually answer it. So, right here, let's say, I don't know, this is where we're going to have to play make-believe for a second. So, right here, I'm going to drag it over. So m is equal to d12 over I12 I24. So if we're going to actually do this question, and you guys will actually have to do it by the numbers, is it always I12 and I24? Yes. Well, okay, it's not always I12 I24. It depends on, so you just have to follow the ends. So if you go back here, it's always for a link, if the output is on link 4, then it's I24. But that slider could have been link 3. It could have been link 7. But the point is that if you follow these ends, that's where you put it. Essentially, you put it on if the output is the slider, you'll put it right here. You'll put I27, right? So just follow these equations. Now they change, obviously, if you have an input of an R2. So if we are sliding something as the input, obviously you have to follow these now. So all new set of rules. So back to this. So essentially, if we, and we're going to do this in a minute. I found a not so clever way of putting a ruler on the screen. And so I'm actually going to measure these out and show you how I want you to do them. However, you're going to use your own ruler for this. Mine is not going to be to scale because I just got a picture and I'm going to put it across it, right? So what they did first was that they found all the instance centers. And because this chapter is about mechanical advantage, they assume you know how to do it already. They didn't do the step-by-step to find instance centers. But we'll just do it really quick. So I12 is right here. I23, I34, and right here at this up and down is I13, right? So that's all of these, or I14. And so this one looks a lot like one that we've already done. We've actually done this question before, except this part didn't exist. It was just a link right here, a Revolut link that didn't have this little part going out. And so they found I24 between the intersections of 2, 3, and 3, 4, and 1, 2, and 1, 4. So once again, 1, 2, and 1, 4, they slid it over here and had it going straight up and down. And 2, 3, and 3, 4 is a straight line right here, so that's how you get the instance center right here. Right? And similarly for 1, 3, they did 1, 2, and 2, 3. So 1, 2, and 2, 3 is this diagonal line. And then, so it's that extremely straight line. And then they did 1, 4, and 3, 4. 3, 4 is on this, and then they just went straight up and down from there. And that is how you get 1, 3 to exist right there. Alright, just to rehash that really fast. So, what I was going to do really fast was I was just going to throw out some measurements, right? So, this right here, we need to find D12. And D12 is shown on the screen to be this distance right here. And like I said, that is the distance from the force being applied to its revolution point, like where it's going to turn around, which is this little pin right here. So, if you took your ruler on the screen, right? If you put your ruler on the screen, or if you print it out and you put your ruler across it, you would find that I'm assuming this right here. This looks at about 1 inch, right? Maybe more, maybe less, right? Depends on how much I, zoom in, obviously, but, that distance right there, we'll say 1 1/4. How about that? So I'm going to say D12 is 1 1/4. So 1 1/4 inches, right? Now, obviously, I can't stress this enough. That is your measurement of your ruler. It is right now, like for example, I could change the whole thing by just doing this, right? Now it's bigger, right? So what I'm saying is that you guys have to use your own ruler there, your own measurements on the screen from the actual problem I give you. So I'm going to give you all the problems like on a Word document. And so that means that everybody's ruler should read the same, right? Don't sit on here and like zoom in and zoom out, because that changes the question for everyone. So I'm expecting everyone to, whenever they get their Word document or their PDF or whatever it is, use your ruler on that. You must have your actual numbers come out of that. So I stated that this is 1.25. So we have this one right here now. Now we need I12, I24. So I12 is right here at this point. And I24, it is up here. So we need to measure that as well. So you would take your ruler and you would place it across the paper and you would find this length right here. Now I'm going to say that that's, you know what, almost double this. We'll say, it's probably around double that. That's what it looks like at least. So we'll say this is 2.5, right? I don't know. But here in a second, I actually have a ruler. After we do this one, we'll move on to that one. So that's 2.5 inches. So then what you do is you plug in 1.25 divided by 2.5, and you get an answer of 0.5, right? Oh shit, what am I doing? So what that means is that, one sec, I gotta go get something. My phone, sorry. So what that means is that for this mechanism, right? For this mechanism, you are getting 0.5. That is the relationship between input or output force to input force. Does that make sense? Which is the equation shown right here. So F4 over F2. And so our input force was obviously F2, F4 is the output. So essentially you are getting 0.5 here. So what that means is, so just what it means for you is that for every 100, for every, like, let's say I put 100 newtons in here, we are getting 50 out over here. Does that make sense? Hopefully that makes sense. Okay. All right, so let me erase this really fast. And I can actually get rid of that as well. I'll do it. All right, so next one up. Now let's move on. So this is the next one right here, which is basically the same. Ooh, one sec. I gotta read this one. This is interesting. The above equations only apply to this life shown in Figure 4. Where's Figure 4? Wait, was that Figure 4? This is due to renumbering of, I don't know. Figure 4. This must be. Is this way up here? Oh, okay. I don't know. I don't know what he's trying to get at here. Okay. Anyway, so I'm not looking at this one. We are looking at this right here. This is what we're about to do. So I have this in my other on my other sheet, and we are going to do this. All right. So this is where we're at. So let me get a certain zoomed in, right? So this is our question, right? So let me get to a text box. So up here we're going to write the steps. So steps to solving mech advantage questions. right? So let's get some steps. So number one, what are some of the steps we can go through? What is the first thing we need to know before solving these? I might actually go up with the font size. That seems really small. Yes, so input output. So right here is F input. This is F output, right? So we know where these two are at. So we need to find the equation to relate those. So really quickly, what are the equations to relate these? So input, come on, come back. Output, force, relationship. So input output relationship equation, right? I need to shut Epic Pen down. So while you're thinking of that, what do you think the input-output relationship is? Anybody? Sorry. So what do you think it is? I'll space down here. So remember, this equation was that it's the force equals force, right? There is no losses. We're assuming no losses. So it's the force equals force equation, essentially. So we have, well, let's number these. Maybe that's the reason why this isn't not clicking. So let's number these, right? So we can call this one what? 2, 3, 4, and 5, right? Did you guys agree? We have 1, 2, 3, 4, 5. These are links, right? These are our links. 1, 2, 3, 4, and 5. All right. So if we were to write this in terms of the force is equal to another force like equation that we did before, how would we do it? So force, input, output. And so how we would write this is that I would suggest we do F input. So our F inputs, we could write Fi times what? D1I, essentially, times WI. You guys remember this, like what we were talking about just a second ago? Anybody? Okay, yeah, so essentially, but we're going to renumber these, right? Because obviously this is kind of a bad way to write it, but I'm writing it in terms of a very generic terms, in vanilla terms. And then we would have force out times D 1O times, and that's D1 output. So this is F force output times D1 output times omega output, right? And then this can then be written further, if we care to do so, as F 2. Although, like I said, you can renumber these in a lot of ways. I think I'll just do, yeah, F2, sure. F2 because we always like to call the input 2, right? So D12 D sorry D12 and then it's omega 2 is equal to F5 D15 times omega 5. Okay. So, does everybody kind of see where these equations... So, like, remember, we just did this in the last part of this, right? Oh, yeah. Okay, I made a mistake. Sorry. This is going to be... Oh, it did... Nope. Can I undo that? I cannot because I suck. So, I made a mistake. Yeah, I should have numbered these differently. I was wondering, I was like, yeah, it doesn't really make sense, does it, how I did it? So this right here should be 3. This should be 2, 4, and 5. Yeah, my mistake. I looked back at that again. I was like, well, that doesn't make sense. It's going to confuse the hell out of people. So, while I rewrite this text out, because for the third time, steps 1, force output to input. Somebody can try and tell me what we should do next. Step 2. Anybody? So this would be F2 times D12 times F. Find your distances, correct. That is definitely what we're looking for. So that would be what though? Our instant centers? Is that what you're saying? More or less? Yes. So find the instant centers and distances required in the equation. I agree with that. So what that means is that what we have to do is that we have to find D12 and D15, right? But we also need to, because remember, this equation right here is not the final terms. It is F5 over F2, and then obviously so you move this to the other side and move this all the way over here. So it should be D12 over D15 over W2, or, so D12 times W2 divided by D15 W5, right? So whenever you have to simplify for F5 over F2, and once you have that, that is mechanical advantage. F5 over F2, it's output over input. And then you have to find everything in the equation, right? And so, everything in the equation that we don't know. We do not know D15, D12, W2, or W5. But remember, W2 over W5 turns into H5, right? Or 1 over H5. Just like the last question, it turns into 1 over H5, which is then an equation we know in the book as like I12, I25 over, you guys remember that hopefully. So, as Jackson said, we need to find the instant centers and distances required. So I'm actually going to write this out. So F5 over F, so it's F5 divided by F2 is equal to D12 times W2 over D15 times W5. So this is our equation right now, right? So this is mechanical advantage, as you remember. F5 over F2 is mechanical advantage. And it's equal to D12 over W2 divided by D15, or D12 times W2 divided by D15 times W5. So we need to find these two quantities, D12 and D15. That is our first goal. So our first goal is that. So D12 and D15. So anybody want to like take a shot at how we're gonna do this? Remember, we need to find some instant centers now, right? Because essentially, D12 is we need to find I12. Essentially, would you guys agree? We need to find all these instant centers. So we need to find what? We need to find our instant centers on this block, right? So let me go ahead and put this up there. I'll just draw it. It's no big deal. So 1, 2, 3, 4, and 5. And just to speed things up, the instant centers that we are going to need, we are going to need I12, right? Although we can find all of them, right? We can probably find all of them. So we can find the ones that we need, though, are the ones that are involved in the H equation and these two distances, right? So we don't need to find all of them. But let's just let's start off. Do we know I23? I23 is located right here at this point. So that right there is I23. And so this right here is different because we've numbered them differently. So 2 would have been usually here and 3 would have been up here, but it doesn't really matter. So we have I23, which is right here. That really squiggly line. Why am I not using the line tool? I'll never understand. Alright. So we have I23. I34 would be where? We do not have I34. What about I24? I24 would be this right here. So this right here is a roll slip, it looks like. Let me see how you move this thing. No, it's not. I don't think this is a roll slip. I think it's just slider. So this right here is what I'm talking about. But anyway, so I'm gonna just draw a line. So right here, remember, since this is a slider, essentially it is on this line at plus or minus infinity, right? But we'll just keep note of that. I don't want it to clog up the thing, but just keep note that right here there is 1. It's between 2 and 4 is right here. All right. This one right here is I51. So I51 is right here. So I51. So I will draw that one. 4-2 we have found. So 4-2 is right here. 5-1 right here. 3-5 don't have. 2-5 we have because 2-5 is inside of here, right? So crap. I might have made another mistake as well. Wow, we're really nailing it today. I was wondering that this must be counted as the ground then. Yeah, I was wondering, this doesn't make any sense. Like, I didn't know how I was going to solve this. Okay. So, it's also this. Yeah, that was dumb of me. My fault. So, right here is 4. Yeah. That is 4. I was wondering, I was like, I don't know how I'm going to solve this, how it is right now. But that makes way more sense. Okay. Sorry for the confusion. It's a Wednesday. So, apologies. So right here, I'm going to draw, although there's not much room, but 4 is that block right there. It's also not colored. All right, so let me get rid of some of these because now we don't have those. So, yeah, this is a rough one. I'm not gonna be able to get rid of all of it, but that's okay. All right, so let's go back to it. So I23 we do have, so I'm gonna put that here. Ugh, dude, why does it keep doing that? Okay. So then we have I45, which is this connection right here. So I45 is known because it's just that revolute pin. But then I42 is this straight up and down slider. See, now it makes way more sense than it was before. So I42 is right here. Essentially, it's at the plus or minus infinity on this line, anywhere this way. So I will leave it for now. I42. What else have I gotten? I31 is right here. I31. It's right there. So I31. We have I51. 3-4 we don't have from what I can see. Is there any obvious ones that I'm missing? Anybody? I think this is it. I don't think I'm missing any more. Two in the slider far right. Oh, you're talking about this? So for some reason, this isn't numbered in any way. Even in the book, it's not numbered. So I'm actually really confused how this thing works. Because I know, so it looks like a slider, right? And as you push this down, this thing slides into here. But it's grounded as well. So I'm really confused. I think this is, yeah, so you would say it's I21, and so I12. You're saying that I12 is over here, right? Somewhere. And I would have been inclined to agree with you, but the point is that for some reason they don't have it there. They have it, I'm about to do that part. But this part right here is confusing because this looks like another link, but they don't label it as a link, nor is it treated as one in this question. So I'll have to look at this one a little more because this right here I don't really understand why it isn't. Because you're right, it should be I21. If this is treated as the ground, it should be that, but I don't think it is. So, yeah, I don't. We'll maybe there's something I have to look at in a second, but not as of right now. I don't see it. Okay, so the goal is that we need to find D12 and D15, right? So D12, we need to find I12. Essentially, I12. So I12 is this right here. Right? So is there any way we can find this right now? Probably not, I would say. So let me draw that. So we need to find this, but I'll change that color. So we have one triangle here, right? So it would be on the line of 2, 3, and 1, 3. So 2, 3, and 1, 3 is right here. 2, 3, and 1, 3, right? But then we have to pinpoint it using another one. So we might not be able to find this one right now. Oh. Okay. Now I see how this works. Man, this question's not... This is not labeled very well. So, Rosendo, you are correct. This is exactly how it is. So they are treating this as the ground. This yellow box that looks like its own link is the ground, apparently. And so I12 is somewhere on this line, right? And so they draw I12 and from here, and they connect it up here, which means that I12 is at this connection. Yeah, that is really strange. I wish they would have labeled that better. Yeah. Okay, well, that's confusing. I'll try to avoid putting confusing things like that for you. Yeah, this is not a very well labeled question at all. So I12 is right there at that point. Yeah, sorry about that. Wow. So I12 is at this point. So essentially what we did is we made this triangle right here, but because they treat this thing as the ground, I12 is on this right here as a slider, right? Or it's on this point as a roll slip or a slider, but we don't know where it's at. But if we know that it has to be on this line and it has to be on a line right here, it means that where they connect, it has to be there, right? So, yeah, well, what a confusing one. All right, and then we need to also find D15, but D15 is right here. So we actually know D15 off the start. Essentially, D15, I'm actually going to draw these out to make it a little more straightforward for you, but essentially, I'll make these black. So essentially, D1, black. D12 is right here, right? And D15 is from here to that point. Although it's not going to be a straight line, but yeah, we already knew where D15 was. But so basically we know both of these now, D12 and D15. So it's basically from this point, the output force, to where it's revoluting, which is right here. And right here, D12 is right here, the input force to I12, which is right here. So you basically, what you would do is you'd take this as a ruler and you'd go across it and get a measurement. Whatever that comes out to be, which I will do in a minute, hopefully, because I have a ruler that I'm going to put across it. I'm going to do it on screen too. It's going to be really high quality. You guys will love it. Alright, so now the next thing that we have to do is we have to break apart W2 over W5. So W2 over W5 is the inverse of H5, and H5 is equal to, let me go back to that right here, H5 is equal to I12, I25, I15, I25. So remember that, because I'll probably forget. So it's, what was this? This is where you guys are supposed to come in now. You're supposed to tell me what I said here. I12, got it. I25. And then this one was I15, I25 again. Yeah, okay, thank you. I25. So, but remember, this is the inverse of that. So essentially this flips to the top. So at the top, it's I15, I25 divided by. So this is inverted, right? So we want 1 over H5 is what we're looking for. So that means we need to find this number as well. Do you guys see a problem with this number? So we have 1, 5. We have 1, 2. We do not have I2, 5. So that means we still need to find I2, 5. So I2, 5 is right here. Green. So I2, 5 is right there. So we need to find it. And it looks like we can do it pretty easily, right? We have I1, 2 and I1, 5. We can make one triangle, so we'll do that right now. So I1, 2, which is right here, to I2, 5, or to I1, 5, which is right here. So essentially it is that line, right? So it's that right here, from here to here. Then that's one triangle, and then we have to find another one, which it looks like I would suggest using 4, 5 and 2, 4. So 4, 5 is this right here. It's this slider line, and 2, 4. And 2, oh no. So 4, 5 and 2, 4 are on the exact same line. It looks like. Essentially. Does everybody see this? Alright, so how you do this one is, so I'm going to get rid of this at the top because this is going to be one of those ones. So you know all those times I promised you where sometimes it might go off the page? This is one of those times. So let me get rid of some of this. Yeah, I'm going to have to get rid of this as well. Yeah, this is going to be one of those times, it looks like. So let me zoom out real quick. So I have to zoom out. So right here, I1, 2 to I'm going to draw this line really, really long. So right there. So I1, 2 from here to 1, 5 is here, right? This long, long line. Then remember, so the next one is 2, 4, which is this up and down one. It is this sliding one, right? Which can be moved. It has to be moved to where we're connecting our other revolute with it, right? So while we do this, let me get rid of this stuff. That's not going well. Anyway, so it's I4, 5, which is this revolute, and 2, 4, which is a slider. So what you do is you take that up and down one, and you move it to the revolute point. And so that would be right there. And as you can see, I still didn't make it long enough. We're just going to call it good, and it meets right here. And that is I2, 5. I'm going to call it good, and it meets right there. So, I2, 5 is right there. We know where I2, 5 is. We know where I1, 5 is. We know where I1, 2 is, right? So now, what we can do is, we can now start, we can play the game. And the game is as follows. So I'm going to draw the lines, although I gotta make that one a bit smaller. Why does it always freak out on me? I will never understand. Black. So that line. And D15 is right there. We're all good there. Alright, so now we can solve the question. So let me pull out the ruler. This is where it's going to get really dumb, and we'll see how well this works. Alright, so as you can see, very small ruler. but now it is very big ruler. See how that works? So, essentially what we're going to do is we're going to do this just like you would on the screen, right? So, remember the equation is D12 times W2 over D15 times W5. So essentially it's D12 times I15, I25. So let's do this first. Let's start. So what I want you guys to do is, because I'm messing with this ruler and I don't want to have to keep resummoning it, when I get a length, type it into the chat for me, please, because it's going to be a pain if you don't. So we're going to start off with D12. D12 is from here to there. So D12 from here to here. So we're just taking rough measurements in inches, right? So what does that say to us? That looks like, what, 2 1/4 inches? Something like that? Anybody agree? So type D12 is 2 1/4, 2.25, or whatever you want to type. I told you this would be high quality. So somebody type that in as we do it, please. I don't ask for much. Everybody's already gone. So D12 is 2.25. The faster you write this in, the faster we can move on. So 2.25. Now let's move down here. D12. But now this right here, it looks like this is what, 1 1/8? Something like that. I would say it's more. It's 1 1/8 more. So do D. Okay. Yeah. So 1 1/8. But yeah, the measuring starts right on this part right here. But like I said, it's only it's gonna be up to you however you draw the lines, because I mean one person's gonna be slightly off than another, and because this is a clip art or a clip, I can't actually see where it starts very well because it goes over it. So we'll do 1 1/8. So D15 is 1 1/8. So type that in. D15 1 1/8. Now we have to do distances such as I15, I25. So D15, 1 1/8. Then we have to do I15, I25. So D1 or I15, I25, which is this bottom part right here. So I15, I25. So I15 is this right here. It's this point, and we have to go all the way up to that. So this is where you would take your ruler and find the right angle here. And so it appears that this one is looking like what? So it's probably pretty close to 7. We could probably call it that, or it could be, 6 and 7/8 or something like that. So I'm gonna call it 6 and 7/8. So 6 and 7/8. All right, which is the distance from this point to this point right here. Now we have to do I12. I25 is equal to, so I12, I25, so I12 is here. So this is kind of like the halfway point. Right here. That looks like 4.5 inches to me. We'll just call it 4.5. I know it's not like quite the exact same angle as how we need it, but we'll just call it 4.5. So 4.5. So now that we have all of that, I can remove the ruler from my presence and we can type in the following answer. So we have D12 over D15. I'm going to parenthesis that off because the H5 part is what we need to also worry about. So H5 or I15, I25 over I12, I25. And this is equal to M, which is also equal to F4 over F2. So if you plug all of this in, so it would be D12 times this essentially. So D12, which we found as, I will 2.25, so 2.25 times, what was I15, I25? 6 7/8, so 6.875. All right, so we have 15.468 divided by the bottom part, which is D15, which we got to be what? Where was, 1 1/8, so 1.125 times I12, I25. And I12, I25 turned out to be 4.5 times 4.5. So this is 5.0625 or whatever, right? So if you do that math, divided by 5.0625, you get about 3, right? So like 3 point something. So 3.05. And what that means is that we are getting a ratio of 3 to 1 from input force to output force. Because remember, input is at the bottom, so it's this. It's F4 over F2. So this is a pretty helpful mechanism, right? I mean, if you were lifting, if you were trying to, let's say that a ratio of this existed for trying to move, 1,000, or let's say 300 pounds, it means that you would have to put in 100 pounds of force to get 300 out. It's pretty good, right? I mean, that's pretty useful, I would say. Yeah, solid mechanism. So, hopefully, I know this was kind of a crap show because of this part right here, but essentially you guys understand how to solve these though, right? It isn't very difficult. This is very low time requirement. As long as you know the equations and how to find instant centers, you guys should be fairly well equipped to do something like this. So, we're going to end for now. I'm going to turn off the old recording.